Hi, linear algebra students. This is the only video you're gonna have to watch in 4.3 and fill in, of course. It's a video that I have to see in your lecture notes. Very important in order to understand what it truly means for a set of vector to be a basis, okay? And it's the unique representation theorem. And okay, let's actually, I'll go through with an highlighter just to highlight what's important, okay? So first of all, it applies to a basis, okay? So if this set is a basis, okay, so U1 until UK, sometimes we call them B1 to BK, like B for basis. So we are given a basis of a subspace S, okay? So this is also important, okay? So we need to talk about the subspace. Then every single vector of S, okay, so this is one important aspect, can be written in exactly one way as a linear combination of the U1 to UK, okay? This theorem is not surprising because bases were invented for exactly this purpose, in order to be able to represent a vector by a single linear combination. Okay. So first, before we prove this theorem, let's actually remind the definition of a basis, because the proof falls from that definition. Okay, so I'll just say reminder because we have seen the definition in class. Okay, so U1 until UK is a basis of S if first, if it satisfies two conditions. So remember that the first condition is that the set is linearly independent. So U1 to UK, so this set is linearly independent. And number two, it spans the whole subspace. So in other words, it is a spanning set for S. So, span of U1 all the way up to UK is equal to S, okay? Now that we have this definition on the board, let's proceed to the proof, which, as I said, is a direct use of that definition, okay? And the proof is very simple. We're gonna take a vector in S, okay? So we're gonna suppose V is in S, and we're gonna prove that for this vector V, there's a single linear combination of the U's. And since this applies for any vector V in S, we will reach the conclusion. So let V be a vector of S, okay? Then, because of condition number two, there is a linear combination in the first place. So that is important to realize. So from number two, okay, so number two, what I mean is like this number two right here. So I'm actually gonna color code it. So from two, there is a linear combination of U1 all the way up to UK, giving V. Okay, so what we mean by this is that V is equal to C1 U1 plus C2 U2, and I will actually not write this, plus all the way up to CK UK. And this is true for some value, of course, C1, C2, etc. So for some C1, like all the way up to CK, being real constants. Okay, so this is from 2. Okay, so we proved that there is a linear combination, but now what's important is to prove that it is the only linear combination, right? Exactly one way. So no more than one way. So what we're gonna do now is we're gonna suppose that there's another one, and we will prove that they must be in fact be equal. So suppose now that like we have a linear combination. So suppose that d1 u1 plus all the way up to dk uk is a LC giving V. Okay. Then what it means is that we can set both sides to be equal. Okay, so what I mean by this is that this thing will be equal to that thing. Okay. So in other words, we can write, okay, well, C1 U1 plus all the way up plus CK UK, okay, is going to be equal to that one linear combination. Okay, so D1 U1 plus all the way up to DK UK. And now what we're going to do is we're going to swing the purple side, right, the purple linear combination, to the other side, okay? And what we're going to get from there is, after grouping all the vectors together, we're going to get, so here I'm going to color code, but we're going to get something in U1 plus something in UK is equal the 0 vector, okay? And what we get here is C1 minus D1, C2 minus D2, and all the way up to CK minus DK. Now, from there, we're going to use the fact that we're going to use number one, okay? The fact that the vectors U1, U2, UK are linearly independent, okay? So from 1, we get that all the weights of this linear combination are 0. So from 1, all the weights of this linear dependence. Remember, it's a linear dependence relation, but let's just say of this linear combination giving 0. So all the weights of this linear combination giving 0 must be 0. So unfortunately, I have to erase here the definition of a basis, but we got what we need. So what does it mean? It means that that's it, like C1 minus D1 must be equal to 0, all the way up until CK minus DK must be equal to 0. Okay, so here we have like C1, D1, and then all the way up to CK, DK. And from there, obviously, we swing the DK on the other side. Well, we swing all the D's on the other side, and we get that C1 is equal to D1, all the way up to CK is equal to DK. What it means is that any linear combination that you could imagine are forced to have the same weight as this one just because of linear independence. And that proves the theorem. That proves that there's a single linear combination giving the vector v. Okay? So any LC of v with like U1 to UK have weights like C1 all the way up to CK. So which means that there's a single linear combination, the one having these weights, right? So there is a single LC of U1 UK giving the vector V, and this is what we wanted to prove. All right, I hope this helped. As I said, this has to be part of your notes. Hopefully you understand the proof, but what's really important is that you remember that the two conditions that are imposed on a basis are exactly made for this theorem to hold, so that we are guaranteed that every element in the set has a representation in terms of the basis element, and only one representation, that there's not like multiple ways of representing elements in the subspace S in terms of that basis. All right, well, see you in class or in the next video.